Hello again, we're in Limits and Series week 2 and we are looking at a picture of what convergence looks like. So we start with some kind of sequence and it looks like it's approaching some kind of value L. So we have this value L that the sequence converges to. And so how do we know? And so the idea is that given any kind of tolerance, so we have a tolerance epsilon bigger than 0. We look and see whether we're within that tolerance of the limit. So we've added the tolerance to the limit, subtracted it to the limit, and we see whether the sequence is in here. And we say, okay, the first few terms are out, but once we get past, say, here, this point here, we are within that tolerance. And that's the picture. Now, of course, the tolerance, any tolerance can be taken. So if we squeeze a little tighter, we have a smaller tolerance, we might have to go further out in order to meet that tighter tolerance. So that the how far out we have to go, will depend on the tolerance. So again, the limit is some number. The tolerance can be anything, and how far out we go depends on the tolerance that we're trying to meet. Here's an example in which we show that a certain sequence has a certain limit. So we want to show that the cube root of 1 over the cube root of n times sine n approaches 0, and this, of course, means as n goes to infinity. That's the only thing that can happen with a sequence, is that we march on along the value of the sequence. So we want to show that xn minus 0, the difference between xn and the limit value, is within the tolerance where epsilon is just some positive number. Now, what do we have control over? We have control over how far out in the sequence we go. So let's do some calculation. And if we look at 1 over the cube root of n times sine n, subtract 0 and take the absolute value, so the 0 doesn't change anything, then we want to show that this is small. Now, I think what's going to make it small is this term here, 1 over the cube root of n. Sine n is between -1 and 1, and so I'm just going to say that. I'm just going to say that this is less than or equal to 1 over the cube root of n. Again, I don't care what sine does as long as it doesn't mess up that the difference between xn and 0 is small. So I'm just focusing on what I think makes it small. Sine of n will sometimes be small and sometimes be close to 1, and I'm not going to worry about it. Okay, great. And so now I have something. I want to show that this 1 over the cube root of n is less than epsilon, and that happens if and only if, well, let's take the cubes of both sides. So this says that 1 over n is less than epsilon cubed, and this happens if and only if n is bigger than 1 over epsilon cubed. Okay, so we figured out why this happens. Let's write it up in a way that agrees with the definition. So let's make it clear that we can meet the criteria put in the definition that show this convergence. So let's do that. Given epsilon bigger than 0, let m equal 1 over epsilon cubed. For n bigger than or equal to m, xn minus 0 is equal to 1 over the cube root of n times the sine, the absolute value of sine of n. This is less than or equal to 1 over the cube root of n, which is less than or equal to 1 over the cube root of m, and this is equal to epsilon because of the choice of m. And so we've shown that given an epsilon, we can go far enough so that when we've gone past that point, everything is less than epsilon. In fact, if this inequality here is actually strict, and of course if n is strictly bigger than m, then this inequality here will also be strict.